the solution is a modified Bessel function. The one that I couldn't think of, so there's other areas like in electric fields and wave equations. So but the case in heat transfer where I can think of, it's when we see this again will be for one-dimensional radial systems, but transient. So we'll have temperature will be a function of R and of time. That we'll see actually Bessel functions, not modified Bessel. Okay, so we went through a lot of this the other day. Scrolling down some more that we looked at what these, some of the definitions for Bessel functions and what they look like. Okay. And here's an example problem to run through, and it will have some Bessel functions in it. And we won't see the math behind it because I'm just going to show you what the equation looks like that has Bessel functions in it. So this is a picture of just a single radial fin, and we've got some dimensions given, and I'll put in, so we think from the center line to, that I just did is R2, and from the center to where the fin meets the tube surface is R1. We've got a thickness given, a base temperature of 110 degrees C, and free stream surrounding air temperature of 35 degrees C. Thermal conductivity for the fin is given, and a heat transfer coefficient. And this problem actually had more parts to it. It was to calculate a fin efficiency. We're just going to do part C. And like our previous fin problem, the only analysis we're doing is steady state. We won't have a transient analysis for fins. Constant properties. Three, no heat generation. One-dimensional radial conduction. Okay. This one I'll talk about for a minute. When we write our temperature as a function of some variables, you might be thinking, and then this is a slice. Let's see, this is a slice through this fin. Here's my pipe. That since I have convection off of this, that maybe if I had, I don't know, so this is my R direction and maybe a Z coordinate, that temperature might vary in the Z direction. But we're going to look at pretty thin fins. We usually have them of relatively high thermal conductivity. So at each location, we can describe temperature. And I keep drawing these straight lines, but I want you, it's not cooling down at the edges. Our assumption that the temperature is uniform at each slice in the R direction. Okay, so we're looking at rate of heat removal from the fin. And the way we're going to calculate that is So this should look like Fourier's law of conduction. So K, a cross-sectional area, and then d theta dr, it's a temperature gradient. So in my picture, again, picture I sliced off the fin, and we're saying any heat that conducts through that fin ultimately has to be lost off of that fin surface, gets convected away from the surface. Okay, so if I look at cross-sectional area, so 2 pi r1, that gives me the circumference, and then my thickness gives me the area. And then we need a few more terms in here. Okay. And these all come from taking the derivative of that temperature distribution. Okay. And this isn't, I haven't derived this. This is, I got this. Well, there was a little bit of derivation, but this isn't something I have shown you. My goal here is to throw in the appropriate Bessel functions and think about how we could evaluate them to get a solution. Okay. The first thing I did, and we know we're going to have to evaluate it for all of these, what I call the arguments, these MR terms, is we need to calculate M. And M is 2H over KT.
Professor, did that derivation come from a previous example? The Bessel?
No, I didn't go through the derivatives. So
Okay.
What we had before, we had a temperature distribution, I think. Temperature distribution. All right. So we would have to take the derivative of this with respect to R. And I didn't show you that.
Gotcha. Okay.
It maybe looks a little bit similar, but let's say we have that equation. Either we'll have that equation, or I will have you practice how you would take a derivative. It's kind of a rote process, but I have not shown that step. Okay. It does show it where our theta b comes in, though. So when we rearrange the equation, we get a theta b out in front. Okay, 2H. And so I'm plugging in numbers that were given in our problem statement. And I'm going to start by evaluating a few of these actually modified Bessel functions. I think I've been just calling them Bessel functions. And I used Excel to do this. So I would take K1 of MR1. And so it's K1. And in that parentheses, I'm going to have this M that I just calculated. and R1 0.05 meters. Okay, so I think I mentioned the other day, I would do equals, oh, in Excel, equals Bessel, and then I take K, and then I need my argument. And this time my order is 1. Okay. These aren't so exciting now that you've seen these. I'll write down one more. So the next one over is I1 of MR2. All right, and we need 0.0 or 0.125. Okay, and I put that into Excel, and that gives me, so now I put Bessel I. We'll show one more. Equals Bessel I. And a 1, and I get 6.408073. All right, so I think you get the hang of it. Let's say we've done all of these Bessel functions out here. Okay. And I want to repeat this equation and show what we're going to put in the first part. So QF is equal to, let's see, I got K, 40 watts per meter Kelvin, 2 pi, R1, thickness, okay, theta B, 110 degrees C minus 35 degrees C, and I need an M. Okay, and then all these terms out here. And these don't have, this is going to give us some ratio. It doesn't have dimensions. So hopefully my dimensions out here. So I'm expecting watt. And I've got a meter and a meter and a meter and a meter. So those are canceled. And I got temperature units. So I do end up with units of watts. And this result is 88.6 watts. Okay. And I'll just put, again, I have only done the first 2 of these modified Bessel functions. I got 6 more I would go through. I do the math. This just comes up with some non-dimensional number. So no units assigned to it. And like you could think that through since it's a ratio. Okay. We've seen an example of a radial fin and chunked in all the numbers for these modified Bessel functions. Okay, there is a handout that I often pass out in class, and I scanned it. I don't think I posted it for you yet. Okay, so I'm going to put table 3.5. Boy, I'm so tired out this morning. I think I meant to do it, but I don't think you have it yet. But it will be in Blackboard. And it says efficiency of common fin shapes. Well, I'm calling it a handout, but obviously I'm not giving it to you. Okay, so it has, and this is a subset of the fins that it has on there, but it has more types shown. So this first one, you've seen that before. You've seen this straight fin with uniform cross section. And then this next one is a triangular fin, a straight fin, but it's got a triangular cross section. And then this last one is another straight fin. So in the Z direction, it has the same shape, but it is parabolic. Okay, and then also on this shape or this table, it has some. Oh, we're coming up to some more of them. Okay, so I'll leave it there for right now. Okay, one of the things that you will notice on this table 3.5 is that all of these fins. You can't tell, but behind the scenes, they have assumed an adiabatic fin tip condition. So, we got maybe convection. We can imagine convection off of that surface. It's a little bit different for these guys because they just come to a point, but we have some other ones. Rather than assuming convection, the assumption in this table is an adiabatic fin tip. And then the way that they correct for the fact that I could really have some convection going on is that they might use a corrected fin length. So in general, the corrected length so LC is the notation our book uses for corrected length. Is to take the length of the fin, and you can see how they noted it, plus cross-sectional area over perimeter. Okay. And again, it's not going to work. We don't use a corrected length for a triangular or parabolic, but a fin that has surface area at the tip, we could use this corrected length. And let's do an example. So for this guy, if I wanted to figure out the corrected length, I would take cross section. Sorry, cross section over perimeter. And cross section is this thickness times the width. Okay. And perimeter is 2 times thickness plus the width. So we're going 2 widths, 2 thicknesses. We're doing that same thing we've seen before, is saying that this is about 0. So our addition to the length to get a corrected length is t over 2. If you were imagining this, I mean, this one I think is kind of easy to think through. They're just saying, I know I got convection off of this whole face. And if I wanted to account for this fact, adiabatic fin tip is an easier condition. We saw the math is easier, comes out a little more simplified. So that's where they like to do that. But now we've left off that I could have convection, but they've added this correction to give us another t over 2 of face area. So in my humble opinion, this correction is usually pretty small, and it just clutters things up. But our book shows it, so I am mentioning it. And I may ask you to do a calculation once. I'll try and be clear whether you should put the corrected length in, just to see how much difference it makes. Okay, for an annular fin. And so this is, we kind of took a slice through an annular fin. So they're trying to show this is our center line, or annular fin or radial fin. They use a corrective length for this also. So if we thought about, you know, this is the surface area that we have convection on, they'll add another t over 2. All right, so this last one is a pin fin, and it has uniform cross section. So again, we could have convection off of that tip surface. And if we wanted to account for this, let's put radial fin. And this goes along with the pin fin. Okay. And just to try this out, so this is diameter over 4. If we used our general rule that it's cross-sectional area over perimeter. So cross-sectional area would be pi r squared for that little face that I colored blue. And the perimeter would be pi diameter, or 2 pi r. So R over 2, or I would get D over 4 for a corrected length. This is a figure I took from our book, and this is for radial fins. So all of these you want to think of, No. These are straight fins, Sorry about that. So we're imagining these stick out of the page infinitely far. Okay, so these are all straight fins. And they are showing this x-axis has corrected length. And they give the corrected length we just talked about for a rectangular cross-section. It gets modified a little bit. But if you look at all of these other two cases, so this is the parabolic, and this is triangular, there is no change to the corrected length. Okay. So just for, I don't know, this discussion's sake, so this AP is the profile area. Okay. And what they're showing, it's easy to think of in this one, is this area. And in this guy, we're looking at that profile area. And they give the equation to how you calculate the fin profile area. I think it's easy in the rectangle and triangle. You'd have to do a little bit of thinking for the parabolic to get that it's the height from the base of the parabolic fin times t divided by 3. Okay. This shows, let's see, they all have, when they're really short, little stubby fins, and we're thinking about efficiency, that is in the denominator, it's that I assume all of the fin surface is at the base temperature to get this maximum. So if I have a little stubby fin, its temperature is pretty close to the base temperature anyway, so that ratio is 1. But as we get further and further, adding more area, you can see, so this is our rectangular. It doesn't do quite as good of a job. Triangular is a little bit better, and then parabolic is even better. But I don't think in practice you actually see these more exotic fin shapes very often. Okay, this is like a little short, I'm going to call it an aside. This is from another book. I have a whole book that is titled Extended Surface Heat Transfer. So all about fins. And because we just saw that picture for the rectangular, triangular, and parabolic pin fin, they have a set of equations that they have optimized the thickness. And so they put a little 0 here to show T0 is the optimized thickness for a rectangular straight fin, a triangular straight fin, and a concave parabolic straight fin. So those 3 cases that we just looked at. Okay, and I keep thinking I'm going to finish this off, but I didn't put this in. So they've already developed that. Okay, so we're just using that result. And then for the length, for the rectangular, and I should maybe do a little bit of introduction so you are thinking. So if we had a certain, so QF prime, that's the rate of heat removal from a fin per unit depth. Okay, so we're doing all these straight fins. If we had a certain rate of heat transfer we needed to remove, and we knew a certain heat transfer coefficient, like we're going to blow over air over it, so we know we could get 20 watts per meter squared Kelvin, or we're going to float water over it, so maybe we're going to get 100. So we also need to know that. We need to know a theta B. So we're saying if we had ambient air, we know what kind of temperature difference we'd expect. And we also, over here, we need to know K. So we've made some design decisions already about what our needs are for this fin. Okay, and then this tells us the optimum thickness and length that we would need to remove that heat, that given heat transfer coefficient, all of those things defined. If we had a triangular fin, it also has an optimal length, and for the concave parabolic, okay, and I haven't forgotten, there's really just like a coefficient of 1 out in front of each of these. Okay. Then if you think about getting the fin profile area, and we just talked about fin profile area, that's sort of the looking side view, tells you something about how much material you will need to manufacture that fin. So for the straight fin, it's just T0 times L0. And we got a whole bunch of stuff to put in here. So we got H squared K. And you can tell I've just multiplied these together. I get a theta B cubed. Well, these are both cubed. QF prime over theta B, and it's cubed. Okay. And the next one, if you remember triangular, I multiply the thickness and the length together, but then I take half of that because you think of this triangular fin, I only need half of that cross-sectional area. And then everything else is the same, H squared K QF prime theta B, and that's cubed. And then we get to the parabolic fin. And this one, we multiply the thickness and length together, but then it's a third of the area. I only liked this chart the first time I saw it, is to think about how much volume of material. If I'm making aluminum fins, you could say it's the ratio of this. If I take my let's see, triangular fin, over rectangular, and think about how much material I'd have to use, which relates directly to that fin profile area. All of these other variables are the same, but it would be this ratio of 0.348 over 0.504, and that is 69%. So I could use a reduction of about 30% of material moving from a rectangular fin to a triangular fin, and I get the same heat removal. I could use the same fluid. Everything could be the same. I could reduce material. Okay. So let's put a note in here if you guys are getting tired out. So this idea behind this was thinking about the ratio of profile areas and indication of material savings. Okay, there's one more point I can make from this slide, and it's looking again at this column in profile area. Again, we're thinking about how that tells me how much fin material I need. If I had to double the heat removal rate for the fin, it means I would need a fin that is 8 times larger. So again, I'm thinking about putting a 2 in here, 2 raised to the power of 3. I need 8 times more profile area. And then likewise, it says something about if I can drive so that I have a bigger temperature difference, if the base temperature of the fin, that we probably can't control, but if I can cool the air off to increase the free stream temperature, that difference is then magnified by a factor, a power of 3. And you can see, so h squared, that's going to, if I can increase heat transfer coefficient, that we're going to get a squared factor. It reduces the profile area. And then using a material that's got high thermal conductivity, which I think you normally think of fins, you want to use something with high thermal conductivity, is also going to reduce the fin area, profile area required. This is moving on to a different topic. So I was talking about fin cross-sectional areas. This is a different quantity, and it's called an overall surface efficiency. Okay, and we're going to put a little 0 to distinguish it from fin efficiency, which we have worked with already. Okay. And this figure here is showing an example of a chunk of a wall that has some fins on it and it has some base area. And the idea is that you could come up with a description for how the overall surface behaves, not just putting together fin efficiencies for individual fins. Okay, so I swiped this slide from somebody else, and then every year I go through it, I have to struggle because it's not my own writing. So we're going to work through this and talk about this a little bit. I like this first chunk here, right? That does a fine job. So this says we want to look at the amount of heat removed from the total surface, and that's going to be what they call is rate of heat removal from the base. So in this case, it's all this area in between the fins. And then we have to remove, and capital N is the total number of fins, and QF is heat removal from a single fin. Okay, so we're summing those up to get the total heat removal rate. Okay, so the next step they do is they've expanded out. So this is heat transfer coefficient, surface area of the base, and T base minus T infinity, and that makes sense. And then this next term, this is the capital N, so that's our number of fins. And then they've written this as the fin efficiency, so eta subscript F, heat transfer coefficient, surface area of the fins, and T base minus T infinity. Okay, so from here, I'm going to stray a little bit. I think I'm doing it a little bit different. So I'm going to combine, what do I have in here? I have an H, I have T base minus T infinity, and I've got left base area plus number of fins fin efficiency and area of the fins. We're leaving the first part the same, T base temperature minus T infinity. Okay, we're going to expand out the base temperature or base area. It's going to be the total area. So if I had this finned surface, I'm looking at all of the outer dimensions of this, and I'm going to subtract off okay, and actually I said that incorrectly. We want all the area. We want the base area, we want the fin area, we want everything. Looking at all this area that air is passing over and removing heat. Okay. And I'm not putting little squiggles on the tip because we're going to assume adiabatic fin tip. Okay. All right, so this combination gave me the base area. So I've subtracted off all of the surface area for the fins, and all I'm left with now, I should be back to the base area. All right, and then this guy is unchanged. Now I can combine this part together. So total area and okay, and we're nearly there. So first part stays the same. Okay. We're going to divide each of these terms in this bracketed part by total area. So now it's going to look like 1 minus okay. And this is the definition for overall surface efficiency. So my last step is I could rewrite this equation is whoa. Okay.
You need an AT up front, right?
I need an AT out front, and they have it over here, so they did it right, and I'm a total. Okay. And AT's not part of overall surface efficiency. Okay. Overall surface efficiency has fin efficiency in it. Okay. So if I was thinking globally, or I don't know, physically, that's a better word, for what this overall surface efficiency is, is you're trying to weight it. The base, right, this area that I keep scribbling blue on top of, that has an efficiency of 1. It's at the base temperature, so it's got the most heat removal rate. The fin surfaces have some efficiency less than 1. And now you're trying to figure out how much of this fin surface is at that is base area and how much is fin, and trying to come up with an efficiency to describe both this combination of base and finned area. Okay, this problem, I think I pulled it out just to give you another way to think about finned surfaces. And if you can see, this has a whole bunch of pin fins, circular pin fins on this surface. And they give us a bunch of details. A little bit of is that we're sitting on this slab of material. So we know a temperature, here it is, down on this lower face. Okay. Then we have to go through this thickness, this 2 millimeter thickness of material. And then the manufacturing process for this finned surface is such that there's a little bit of a thermal resistance. However they embedded these into the plate, there is a little bit of thermal resistance for each of the fins. And then we got the fins, and that's back to thinking about heat removal rate for those finned surfaces. If I was going to draw a thermal resistance network for this surface and come up with how much heat I can pull from that that finned surface, so I'm starting with the base, and I guess I called this R the base. Okay, and we're thinking that's this little 2 millimeter slab of material. But now I have 2 paths for heat to be convected away from that surface. So one is that I have to go through a contact resistance. And then I go through the fin. And then the other path is that I am not past, I'm on the unfinned portion of the surface, and I can write a thermal resistance element for the unfinned section. Okay. And we could assemble this to get a overall thermal resistance for this combined section of, some of the heat going through the fins, some of it going through the unfinned base area. The base area, the thermal resistance, L over Ka is my general way of thinking about it. If I put it in terms of this problem, it's a TH, they did 2 letters, thickness B, so that's all thickness, and KB and area B. if I looked at contact resistance, and in general, looks like, I always think that double prime means per unit area already, but when you watch the units, you'll see you got to divide by area. And if I was going to write that in terms of this problem, they wrote it as an R contact double prime, and then I have to put in the total area. So it's the number of fins that I have, and it's cross-sectional area of one fin. Okay, what do we want to do next? Ooh, the fin. Okay. So I'm trying to think of ways I can come up with this. And if I go back to kind of the definition for a thermal resistance, it's the driving temperature difference over rate of heat transfer. And I'm just going to put, and it's not TB to T infinity. Let's just leave it as it would be whatever this temperature is over here. But I'm just going to leave it as a delta T, and Q for the fin as eta fin, number of fins, surface area of the fin, a heat transfer coefficient, and delta T. Okay, so that gives me total surface area for the fin. This would be for one fin. And then the last resistance we have to look at is for the unfinned surface. And in general, I think of 1 over HA. Okay, and this one really, it's just coming up with that area. So H, we are given that for this problem. And A base minus however many fins we have, and cross section of one fin. All right, I worked through more details on this to get to a final solution, but I think we really set up the parts I wanted you to see from this. So after that's a bunch of chunking numbers in and working through. And again, hopefully you're thinking that if I wanted to solve for how much heat I can pull out of this finned surface, I have to put in all the details to solve for each of these thermal resistances. Okay. But it would be back to a thermal resistance network problem, which you have seen before. Okay. We talked about this other day because I was all excited that your review problem kind of showed this rule for when you can assume 1D conduction for fins. But I'm going to hit it again it's a guideline for when you would assume 1D conduction. You have this idea that now that you have numerical methods, again, I keep drawing these fins, but this is going to be my plus x away from this. And I could really solve for the actual temperature throughout these fins. But our analysis assumes that I have temperature only a function of x. It's not, let's see, if I think of this as temperature increase and I'm looking at a particular location, you would imagine it actually does cool down at the outer face as I've got convection off of it. But our assumption is that that change in the y direction is so small because it's usually a high thermal conductivity material. It's a pretty thin fin. We want to get lots of surface area. Okay, so we want to talk about, you could do 2D. You could do 2D, but this is a simplifying assumption. We get analytical results. Okay, I'm putting this bottom that the resistance is moderate. It's really a ratio between these two. So you want the top one to be relatively small. You want the bottom one to be relatively big. Okay, and the case that we're looking at is we want, I'm going to draw this even bigger. And I'm going to put my x-axis this direction, y direction up here. And again, I'm picturing I've got heat being conducted along this fin, and we've got it being convected away from the face. Okay. So the resistance I want to be small is lateral conduction. And lateral conduction means how it's conducting away from this center line. Again, we'd like to be able to have this uniform temperature throughout. And if it takes a long time, if it's slow for it to move away from this center line, it is unlikely. So I want low resistance. And then the resistance that we want to be moderate So this is my lateral conduction. Okay. So the other thing that would be problematic, if I had really high heat transfer coefficient and I had a fluid that was able to pull heat off of the surface really quickly, it would be hard for this fin to keep pumping heat in the lateral direction to make up the heat loss at the surface. So we want that resistance. So we don't want heat to be able to be pulled off of this fin super quickly, because we want the heat to be able to become nearly uniform through the cross section. Okay. So we want this convection resistance to be moderate. So it's not pulled out really quick, not a really small resistance. Okay, so we did this the other day, resistance to lateral conduction. So that's a conduction problem. And so if I had this as, what do you call that? this is a thickness of the fin. Okay, so my lateral conduction is T over 2, half the thickness from the center. This can conduct this direction, so I really only care about a half thickness that I have to conduct heat through. So L over Ka. Okay, and just reminding you, so normally I think of this as an L over Ka. I put my 2 in the denominator. Okay. And for convection, 1 over Ha. Okay. So that combination of variables is what I'd like to check. And I would like to see that it's a small number. And the rule of thumb is that we'd like it to be less than 0.1. So we're saying that the resistance to lateral conduction is 10 times smaller than the resistance to convection. Okay. This next slide that's coming up, so this picture says ratio of 2D to 1D fin efficiency solutions. Okay. So the part we just talked about is assuming one-dimensional fin model. And then if we did a finite element or finite difference solution, we could come up with a 2D solution. And looking at those two ratios, and they plotted as a function of Biot number, which we just talked about. So for 0.1, I'm going to say that's 0.1. The two solutions, a 2D and a 1D, we do a really good job. Those two solutions are nearly the same, but it falls off as Biot number gets larger and larger. Okay. So I think my idea for showing this slide was just to say, we did a little bit of calculation, and I told you what this rule of thumb was, and just demonstrating that some people have calculated this ratio and why a ratio of 0.1 is acceptable, because you're coming close to the actual case. You really know that you're likely cooling the fin off by convection. It's not quite 1D, but it does a pretty good job. Okay, one more thing I wanted to show you. Okay. This is not in your slides, okay? And I thought about adding it, but I did not. Okay. So this is an example of a fin, and actually it looks a lot like one I had the very first day of class when we started talking about fins. Okay.
Professor, we're looking at the presenter view right now, not at the presented.
Okay. So what does that mean to me?
If you go at the top where it says display settings, I think you can flip the presenter and the presented view.
So you're saying you can't see my picture right now?
No, we were seeing the presenter, the other side, the other view, the other PowerPoint view.
Okay.
Sometimes when you have two screens on PowerPoint, it shows like a presenter view where it shows like the next slide that's coming up and any notes that you had on the slide. That's what we were saying.
Whoa. Okay, I get what you're saying now. Okay, well, my picture's gone now, but you saw it. You saw it, right? So let's say, and this was, I often have, well, if I was in person, I would show you. I have a little fin, and I'd show it to you in two orientations. So if you go to look at catalogs for fins, they will give a thermal resistance for this heat sink. And, you know, I didn't find it for that exact one, but let's say, for example, and so I hope you kind of know how you might come up with that. Again, picturing that chunk of material that you just saw, that I flipped up for a minute and then I lost it, and you hopefully you're visualizing what the thermal resistance for that element looks like. Okay, and they give you, you know, it will say like you're blowing air over it at a certain speed, and it will give that thermal resistance. I didn't spend a ton of time looking. Most of the ones I saw today did not give the resistance value for free convection. And I know that's like a little bit mushier because you don't know how much heat you're pushing through that. So maybe that's harder or less reliable data. But I was kind of interested in seeing that. Okay. And then one catalog I saw showed, so they gave a value, let's say like thermal resistance is 0.9 in a vertical orientation. And let's say vertical, this is my fin, the base, and I'm not going to be able to draw these fins. I mean, there were many fins. So this is my base surface. Okay. And then this is horizontal. Okay. Can you think through, do you think the resistance would be higher in the vertical orientation or in the horizontal orientation? And let's think through, this is for free convection.
I think vertical.
Would be higher.
Higher.
Okay, so happy you spoke up, but this is, and I'm looking at, you didn't see what fin I'm talking about, but this should hold across different types. That horizontal is a little bit higher thermal resistance. And if you think about it, in this case, I could have air, you know, it gets heated up by these fin surfaces, and it can move through that, that fin array, and cool air can be moving in. But in this case, the heat moves up over these fin surfaces. It has a tougher time. You know, it's maybe coming in from the sides, but it's a little bit less effective to get cool air into this horizontal orientation. So it's got a little bit higher thermal resistance. So that was my attempt to have a little bit of practical ending for fins. And I started, I posted lecture 6, but I think we're close enough that we'll call it a day. And so I am going to, I'm trying to think real quick, did I want to say anything else? You guys are working on homework 3, and you have an exam on Monday. I think that's all I wanted to cover, and we'll just hang out and see if there are some questions.
Thank you.
I know you went over for the people who stayed after last class, but do you want to go over the exam notes again?
I'm sorry, a plane was going over and I couldn't hear the first part you said.
Oh, I said, I know you went over for those of us who stayed after class last time, but did you want to run over the same notes regards to the exam content and structure with equation sheets and stuff again?
Well, so you're doing better than I did. I don't remember I went over that after class. What did I say after class?
Open book, the fact that we could prepare a equation sheet if we wanted to, that kind of thing.
Oh, okay. And so I haven't told other people that. Okay.
Correct.
Okay. Okay, so open book. Oh, I know some of you have electronic versions of the book. I'm gonna walk around, and you guys know the gig. I hope you're not like scrolling around to your homework sets or whatever. You should be using the book. You can prepare an equation sheet in it, just because I know I have to put some bounds on you. But on the equation sheet, it should just be equations you use, maybe something where you remind yourself, if I need to find this equation, it's in this table or it's on this page. It should not be worked out problems. You should bring a calculator. I don't know, how much do you guys use calculators at work?
Rarely.
Sometimes, okay.
Most
My
of it can be done with
calculators-
Excel.
I am
Okay.
frequently using the TI-83 emulator on my phone.
Okay. Oh, okay. Do you have a calculator?
Yes, I have an actual TI-83. I just don't bring it to work most of the time.
Gotcha.
Or I use
Okay,
Excel
so
like a
that
normal
is
person.
Yeah. That probably is something to hit harder, because I think students here are walking around with their calculators, but I get that may not be a normal thing for you. So it is up to thermoresistance networks. The fin content is not part of this exam.
Is the formula sheet front and back?
Yes. All right, and you guys know that we're meeting in person. You come to that engineering classroom in building 35. We should be able to spread out reasonably well. I think I might have both sides of that room. Oh, yeah. 5:15. 5:15. Yeah. I've known that. Andrea told me that like right away, but maybe I haven't been hitting that very hard. Yes, it's a different start time. Sure.
Do you have any advice for what we should be studying? Like if we could work through all of the homework problems for homeworks 1, 2, and 3, would you say we're in really good shape, or it's going to go well beyond just what we saw in homework?
So I would like that you work homework. So if you had, you maybe see sometimes I write a little bit more on the solution. Like I'll say, and if you integrate this, you'll see how much heat leaves. Anyway, that's the kind of stuff I hope you guys are doing when you work homework. You're thinking, I wonder what happens if I do this. What if so I would like most of to be things that you have seen before with maybe just a little extension. But if I could come up with it, I don't know if I will, I would like something that's a little bit of a stretch. Okay, so yes, I would say working homework problems. Sometimes I do problems in class. That might be another source. Sometimes there are problems in the book. That would be another source. There's some concepts I can think of. I guess I'm just going to, what's the one I can think of right now? Do you know what has to be true to use a thermoresistance network? So sometimes I have some questions.
Are you
In
talking
terms of problem structure, is it going to be like the homework where it's 3 or 4, full format, here's your givens, do the whole calculation, or are there going to be some like smaller mixed in, like you just mentioned, like, oh, what is necessary for this to happen, kind of either short response or multiple choice type sprinkled in as well?
Okay. It's likely there's going to be some short. So I think there's going to be 2 longer problems and then some short stuff. And I guess I'll mention, I am a stickler. I really like that you do your homework and you show all the steps. Like I like when you tell me what you're going to find. You might use no, you don't, because I don't do it quite the same for your class. But what you're supposed to find, what you're assuming. I don't care so much on the exam. I would say I really do like that you start with an equation in symbolic form and help me follow the solution. But I don't request a certain format. You can just get going. But I would like a logical solution shown.
And I'm assuming you give partial credit, and like, what if we miss an assumption? Are you going to dock us on points for that?
Why, certainly. I'm being a little bit flippant, but it's like, yeah, if there's something that you should have gotten from the problem and you missed it, to me it was pretty clear that was, yeah, that will be some deductions. All right, it still looks like people are here, so I'll hang on.